Now to solve that problem, remember we want the derivative to be we want to ultimately compute the derivative, right? So what we want to consider is what happens when I perturb S by an infinitesimal amount. So my delta J as a response to an infinitesimal perturbation in S is the following. Is actually partial J partial U times UN times a delta UN, right? That delta UN is the perturbation in the UN as a result of an infinitesimal perturbation in S, plus a U hat of N, which is whatever it is, times delta UN minus now a perturbation of this function is partial UN minus 1 times delta UN minus partial UN partial S times delta S, and etc. Okay, let me just write a little bit of more terms just to make it clear what the cancellation would be. So the next term is this times delta UN minus 1 minus partial UN minus 1, UN minus 2, delta UN minus 2, right, plus dot dot dot, and finally I have U0 hat delta U0 minus actually du0 ds delta S. So borrowing the idea from our very first simplistic example, we want to be able to compute that delta J without having to compute the solution or the change in the solution again and again. Specifically in this case, what do we want to avoid having to compute? So if my S has many dimensions, I want to evaluate my delta J for arbitrary change in S, right? I want to compute so effectively the task of computing the gradient is really being able to compute delta J for arbitrary infinitesimal change in S, right? What do we want to eliminate in this large expression? And by the way, here, this equation is true for any U hat 0, U hat 1, U hat n, right? This expression is true for any of these hat functions. So can we use the fact that this is true for any values of these and cancel some of the terms we don't really want in our formula? Not have to calculate delta UN minus 1. Right. The first idea is I can choose U hat n transpose equal to dj du. Then I don't have to compute UN minus 1. But then I still have delta UN. Then I don't have to compute delta UN, but I still have delta UN minus 1. So what should I do then? Yeah, I can choose U. I can, oh, here is a negative, right? So, but then I can choose U hat of n minus 1 transpose equal to U hat of n transpose times dun minus 1, right? Do you see this is exactly the backpropagation algorithm we just derived? All right, so by having this, we eliminated this and this, and we can keep going, right? So this we have eliminated the need of evaluating delta UN minus 1, and we can keep going. U hat of n minus 2 transpose can be U hat of n minus 1 transpose times dun minus 1 dun minus 2, and etc. all the way when we want to cancel delta U0, then we have to set U hat 0 transpose would be equal to U1 hat transpose times d U1 du0. So with all of this, all the delta u's are cancelled, and my delta j would be left as what? It'll be a direct function of delta s, right? All the terms that involves the intermediate delta u's are cancelled, and the resulting delta j is just a summation of I goes from 0 to n of U hat I transpose times partial UI partial S times delta S, just like our first example. My delta J in the first example is very special in that my J can be expressed directly as a function of S. In more general cases, I can't do that for the nonlinear function J, but I can express any infinitesimal perturbation of our objective function directly as a function of an infinitesimal perturbation in the design parameter, no matter how complex the intermediate steps are. All right. So that's again the back propagation derived using a slightly different way, but that slightly different approach can be used exactly even on the continuous case, on the ordinary differential equations. Actually, you can see that as I go through the math, you see the derivation for the differential equations actually turns out to be slightly clearer than the huge formula I have to go through for the discrete steps.